Today we are going to take up some special topics in vibrations of beams. So, the first topic that we are going to discuss is that of a tensioned beam. So, what happens when a uniform beam is subject to tensile loading? So, this is important because when we discuss strings, taut strings are in tension, but as we have discussed before that there are examples, for example, the guitar string which looks like more like a beam under very low tension, and as you make it taut it becomes a string. So, we are going to look at this in this transition of behavior from a beam like behavior to a string like behavior when you put a beam under tensile loading. So, let us look at this example. Let us consider this Euler-Bernoulli beam. Which is subjected to a tensile loading, say T. Then the equation of motion So, this is an Euler-Bernoulli beam. So, these two terms are from the beam equation. Now, when you have this tensile loading, then additionally you have so, this is the equation of motion for an Euler-Bernoulli beam. In case of a so this is for an Euler-Bernoulli beam. In the case of a Rayleigh beam, you have this additional term because of rotary inertia. So, this is for a Rayleigh beam which has this additional term because of the rotary inertia. Now, since this can always fall back to the Euler-Bernoulli beam if you drop this rotary inertia term. So, we can discuss the Rayleigh beam. So, let us first non-dimensionalize the equation of motion. So, if you do this non-dimensionalization using this scheme. So, the spatial coordinate is non-dimensionalized with the length, whereas the field variable is non-dimensionalized with this r g, which is the radius of gyration which is defined as square root of the second moment of the area divided by the area of cross section. Further, we non-dimensionalize time using the speed of propagation of transverse waves So, if you use this non-dimensionalization scheme, then the non-dimensional equation of motion turns out to be in this form. Now, here we make so now you see that these two terms are from the string equation of motion, whereas these two terms are from the flexural stiffness and the rotor inertia. Now, if you look at these coefficients, so these coefficients this can be written if you divide the numerator and denominator by rho a, then I can recast this as where epsilon is obviously the axial strain in the beam. So, T divided by E A. So, that is going to give us the strain because of this tensile loading, and S R is defined as the length over the radius of gyration. This is known as the slenderness ratio. So, this is a slenderness ratio, and this is the axial strain. Now, so this coefficient is nothing but inverse of the axial strain and inverse of the square of the slenderness ratio. Similarly, this coefficient is 1 over slenderness ratio square. Now, using these definitions, then we can rewrite the equation of motion So, this is our equation in non-dimensional form, and the parameters and the coefficients defined in a very special way. So, here I have of course dropped the tilde symbol for simplicity. Now, let us look at these terms. So, this is the slenderness ratio, which indicates how slender the beam is. So, it is the length over the radius of gyration. So, if the beam is very slender, then the slenderness ratio is very large, because its length is much larger than the area property. So, when the beam is very slender, then this is very large, and therefore, these terms can be dropped in comparison to this term. So, in that case, we expect a string like behavior. So, in other words, we can treat a beam under tension, a very slender beam under tension, like a string. On the other hand, if this strain is very small, so the axial strain is very small. So, if the tension is small, and the axial strain is very small, in that case this term might become significant. In that case, you may have to include this flexural term in the equation of motion. So, this rotor inertia term therefore, is negligible in the case of slender beams, whereas this term is negligible if the beam is again slender and the tension is very high. So, the tension is very high and the beam is slender, then these two terms can be dropped. Therefore, it will have a string like behavior, or the system can be modeled as a string. Whereas, if tension is very small, then this flexural term may be significant. So, this must be considered. So, you tend to more like a beam like model. So, this is precisely what we observe from this equation, and elements like the guitar string, which are extremely slender when they are put, even though they have sufficient bending stiffness, but when they are subject to a large tension, in that case the behavior is like a string. So, you can treat a guitar string under tremendous amount of tension as a string. So, this is what we have observed. So, another way to look at it is that the restoring force in a restoring force in a guitar string is more because of tension than because of its flexural rigidity, so or flexural stiffness. Next, let us consider a beam with non-homogeneous boundary condition. So, in various situations you find beams which are excited at the boundary. So, for example, when you have an absorber attached to a vibrating structure, an absorber made of a continuous system like a beam which may be attached to a vibrating surface or a structure for the purpose of vibration absorption. So, usually these beams are like cantilever beams. So, they are fixed on the structure and they vibrate because of base excitation. So, let us consider this example of a cantilever beam So, this is a cantilever beam which is subjected to base excitation. So, we can consider that this motion of the base is given by h of t. So, this is a time varying function which is specified, let us say, and we will consider that this is an Euler-Bernoulli beam. So, the equation of motion is given by this, and the boundary conditions So, the displacement of this boundary suppose is given by this function h of t. At x equal to 0, we also have this condition that the slope is 0, whereas for the free end we have the bending moment as 0 and the shear force. Is 0. Now, if you have, so this is one kind of non-homogeneous boundary condition. You can have other kinds. For example, you can have a cantilever beam once again, but let us say with a time varying moment at the free end. So, in this case we can write the equation of motion and boundary conditions So, once again at this free end now they are both 0, the displacement and the slope, whereas the bending moment at condition at this free end may be written like this. And the shear force at the free end is 0. So, this is another kind of non-homogeneous boundary condition where you have the force. Here it was the displacement, here it was the force. Now, when you have force, it is possible to include it in the equation of motion. So, so we are going to first discuss this this kind of system where we have excitation, boundary excitation in terms of displacement. When you have forces, again it is possible very easily to include this force in the equation of motion, and then we can treat it as a system with homogeneous boundary condition. Now, why do we need this? Because whenever we have solved the eigenvalue problem, we have considered homogeneous boundary conditions usually. So, if you want to use this modal expansion theorem for solving the system, In such cases, you will require that the boundary conditions be homogenized first. Otherwise, the modal expansion, the eigenfunctions do not satisfy will not satisfy the boundary conditions with time varying functions. So, we would like to have a method of homogenizing the boundary conditions for the problem. So, let us look at this problem first. So, we have this cantilever beam with base excitation. Now, let us try to make a transformation of variables. So, let us say that our field variable W, we want to convert or transform to another field variable, let us say u x comma t plus an unknown function of x times h of t. So, which is this function that you have as the forcing. Now, this structure is of course motivated by the structure of the boundary conditions. Now, if you consider this this new, so this is a new field variable, and this function is as yet unknown. So, this is an unknown function. Now, let us use this this transformed this transformation in the equation in the boundary conditions. So, the displacement boundary condition so this must be h of t. The slope condition so prime here denotes derivative with respect to x, that must be 0. Now, the bending moment condition is 0, and similarly the shear force condition at x equal to L is also 0. Now, we would like to have, so this is our new field variable. So, the equation of motion so if you substitute this in the equation of motion, that is equal to minus of rho a eta h double dot that comes from the inertia term, and similarly this comes from the flexural stiffness term. Now, we would like to have homogeneous boundary conditions for this equation of motion. Now, the field variable is u, and the right hand side is now we have in terms of the time varying function h and as yet unknown function eta. So, if you want to have homogeneous boundary conditions for u, which means that this must be 0. So, these are all 0. So, this implies eta of 0 is 1, Now, we have to construct a function eta which satisfies these 4 conditions. Now, to keep things simple, we can consider a polynomial in this form, and if you now use these conditions, so this will imply a 0 is 1, eta prime 0 is 0. So, this will imply a 1 is 0. Eta double prime L, if that is to vanish, then twice a 2 plus 6 a 3 L must vanish. And if the triple derivative of eta is to vanish, then a 3 must be 0. So, in that case a 2 is also 0. So, therefore, eta is nothing but 1. So, this is a very simple example. So, in that case finally, and therefore, the equation of motion so what we obtain from here so this is the equation of motion, and this is accompanied by boundary conditions which are all homogeneous. So, these are the boundary conditions. So, we have now a system which is forced, but has homogeneous boundary conditions. Now, if you perform therefore, the modal analysis of the unforced system, which is nothing but a normal cantilever beam, then you can use the eigenfunctions of the unforced system to solve the forced vibration problem. So, we can easily convert any non-homogeneous problem with non-homogeneous boundary conditions to problems with homogeneous boundary conditions. Next, let us look at this important phenomenon of damping. So, as we have discussed before as well, we can have two kinds of damping in continuous systems. One is the external damping, which is more common or very easy to see, and then there is an internal damping which is very actually hard to model and also very less understood. This is because it depends on the material constitution, the internal structure of the material. Now, this internal damping we are all considering throughout one dimensional elastic continuum. So, beam is also a one dimensional elastic continuum. So, the source of this internal damping is usually friction between the layers of the molecular layers inside the structure or inside the material. So, when we are saying we are considering one dimensional continuum, then there is no question of having layers. So, we must introduce this internal damping in a phenomenological way. So, to do that we follow the Kelvin-White model. So, let us look at this model for internal damping. So, first we are going to look at internal damping. So, to model internal damping, we use the Kelvin-White model. So, this in order to implement this model, we modify the constitutive relation of the material. So, we know we have used that for our beam model the Hooke's law given by the stress equals the Young's modulus times the axial strain. So, this was the axial stress in the fibers of the beam. Now, in addition to this the stress because of the mechanical straining, we add a second term which is dependent on the strain rate. So, the stress not only depends on the amount of straining in the fibers, but also the rate at which the fibers are being strained. Here this eta is known as the loss factor. It is written in a special way in order to match this term. So, E times some eta times epsilon dot. So, if you use this model to derive the equation of motion, then you can easily see that the equation of motion so these are the two terms that we already have in the Euler-Bernoulli beam. Now, because of this additional term, you can expect that there is going to be so this is the new term because of internal damping. Now, to see that this is really a damping term. So, we multiply this whole equation with the velocity del w del t and integrate over the domain of the beam, that is the length of the beam. So, we obtain and integrate this and that must also be 0. Now, we integrate by parts this term 2 times. So, and similarly this term also integrate by parts 2 times. And the rest of the terms in the, so in the integral I can write this term as similarly after integrating by parts this term 2 times so this is what you are going to get. Now, if you use the boundary conditions, say for example, in a simply supported beam, then at L the velocity must be 0, at and the bending moment must be 0. So, this term will vanish, similarly this term will also vanish. So, using the boundary conditions you can show that these boundary terms will actually vanish. So, therefore, we are left with this integral equal to 0. Now, you can easily identify that this term, these two terms is nothing but the total energy, the rate of change of total energy. Half rho a del W del T whole square is the kinetic energy, this is the potential energy. So, this is the total energy, and this term I am going to take on the other side. Now, if there is an eta as well, so now E is positive, I is positive. If eta is also positive and this is a squared quantity, so this is a positive quantity. So, integrated over the length of the beam, so this must be positive quantity if eta is positive, and therefore, the energy, the rate of change of energy is negative, which means that energy always reduces. So, if this loss factor is positive, then this term is going to drain the mechanical energy. Now, let us look at now simply supported Euler-Bernoulli beam with internal damping. So, So, the moments are 0. Now, we have seen that for an undamped beam, the modal vibration is given by let us for a moment assume that this beam is vibrating in this nth mode. So, if I substitute this in the damped equation, then I can rewrite if you substitute this in the equation of motion and simplify, if you simplify, then so this can be in general a function of time. You can recast the equation in this form, where so this is what is interesting to observe. So, if you consider that the beam is vibrating in the nth mode, then the equation of motion for that mode, the modal coordinate, the modal dynamics is governed by this equation, where the natural frequency is as expected, but there is a damping factor which we find is proportional to n square. So, higher the mode, higher will be the damping factor. So, which means that the higher modes get effectively damped because of internal damping. You can repeat this analysis with external damping, and you can easily show, and this we have seen before as well in the case of strings and bars, that with external damping the lower modes are more effectively damped than the higher modes. Same conclusion can be drawn even for this beam vibration, where we find that internal damping is effectively damping the higher modes and the external damping will effectively damp the lower modes. So, to conclude today what we have discussed, we have considered two topics from beam vibrations, three topics. So, first we have considered the non-homogeneous, we have considered non-homogeneous boundary conditions, we have considered internal damping in beams, and in the beginning we also looked at the beam under tension. So, how the string and the beam behavior gets delineated. So, that was another topic we looked at. So, with that we conclude this lecture.